The following video is intended to give understanding regarding vectors geometrically. So we probably should understand what a vector is. A vector is represented by an arrow with both direction and magnitude. So we're really just looking at some quantity that has direction and magnitude. There is such a thing called a position vector. And a position vector does have a specific location. So if we took a vector and we moved it, say, for example, to the origin, a lot of times that will help with understanding regarding vectors, but we're not going to be talking about position vectors today. We're just going to be talking about vectors in general. So the only thing we're really looking at is direction and magnitude. So what happens then if we had a vector? We'll say that this is our vector right here of vector A, and we're going to add this vector A to vector B. So I want to know what vector A plus vector B is. In fact, a lot of times for understanding, a lot of times the notation for a vector is to put a little arrow above the letter indicating that this is not, say, a length, and we also have a direction as well. It's not just a magnitude, it's a direction. So I'm going to do the same thing here. So we'll say that vector A plus vector B, we're going to do this all geometrically. So what I'm going to do is I'm going to move these vectors so that they line up from head to tail. So this is vector A, and then the vector B, this is 2 over and 3 down, so 2 over 3 down. So this is our other vector here of vector B. And we add these two vectors together, and this is going to give us what's called a resultant vector. The resultant vector is going to start at the tail and go to the head. So our direction is in this direction right here. So the idea is if we had, say, a sailboat, and we'll say the sailboat is here, and the sailboat is being, well, there's two vectors acting on it. One vector is wind, and the wind is pushing us in a certain direction. We have another vector, say an ocean current, pulling us in another direction. So both of these vectors acting on our boat simultaneously would move our boat along this line right here. So there you go. This line here would be vector A plus vector B. And it doesn't really matter the order because, again, position doesn't matter. So it is also true if I take vector B plus vector A, we're going to get the same resultant vector. So our first vector, B, is going to be 2 over 3 down, 2 over 3 down right here. This is vector B. And then we're going to take this other vector, we line them up from head to tail. So this is our tail, our head here. So we're going to line up the tail, 3 over, 2 up, 1, 2, 3 over, and 2 up, gives us this other vector here. So together, this vector plus this vector, we have both of these vectors acting on our sailboat, pushing us in two different directions simultaneously. So what you're going to see from an outside observer, we're going to see this vector, we're going to see the sailboat sail in this direction here. So we can see that our resultant vector is still going to be, both of these are 4 over and 1 down. So what happens, one other thing we need to talk about is scalars. So if I had something like, if I wanted to, say, have 2 of these vector A's plus 1 of these vector B's, then we're basically taking 2 of these, the magnitude and directions. So if we have this vector A here of 3 over 2 up, 3 over 2 up, and 3 over 2 up, this is going to be 2 of vector A plus vector B. B is 2 over and 3 down, 2 over 3 down. So this is our other vector here of B. So in this case, our resultant vector is going to look like this. This vector here of 2, 4, 6, 8 over to the right and 1 up is 2 times vector A plus vector B. So we're going to do a bunch of problems now relating to vectors, and hopefully this will give a better understanding of what vectors are in general. So these problems have been taken from an IB textbook. And we see that the first one says, I need to state the vector which are equal in magnitude. So if we're just looking at the magnitude, we're looking at the length, I'm going to argue that, well, this looks the same length as this, which is the same length as this. So if we're just looking at the magnitude, we're ignoring the direction. So vector P and vector Q and vector S all have the same magnitude. What vectors are parallel? Well, if they're parallel, direction also doesn't matter. So we're looking at vector P, Q, and R. Those are all parallel. I want to know the vectors that are going in the same direction. The only two vectors that are going in the same direction are P and R. They're both going up. So P and R. What vectors are equal? Well, if the definition of a vector is magnitude and direction, then if vectors are equal, it means that you have two vectors that are going in the same direction and they have the same magnitude. And in this case, I don't see that we have any equal vectors at all here. Oh, I'm sorry, I see one over here that I've completely ignored the whole time. It looks like this vector here is also going to be the same size, so we're looking at T here. Parallel, this one is also parallel, same direction. It looks like, well, so P and R are going in the same direction, and Q and T. Q and T are both going in the same direction as well. So as far as the vectors that are equal, the only vectors here that I see that are equal with the same direction and the same magnitude are Q and T. So Q and T. Next one says the negatives of each other. Well, a negative vector, if I have a vector P and then the negative vector would be negative P, that means that a negative vector means you're going in the opposite direction. So in this case, so if we're looking at a vector that's just negative of itself, of the previous vector, then the magnitude still has to be the same. So it looks like to me that P and Q, the same magnitude, opposite directions, so we're looking at P and Q. Let's look at the next one. So for the following problem, it says the figure alongside consists of two equilateral triangles. Equilateral triangles means that the lengths of all of the sides are the same length. And then we have A, B, and C. They all lie on a straight line. And then this length here of AB is represented by vector P. We have this vector AE, which is represented by vector Q. And we have vector DC, which is represented by vector R. So which of the following statements are true? Is the vector EB, is that equal to R? Well, they're both going in the same direction. They're the same size. So yes, it's true. The next one, if we have these absolute values around a vector, it means the magnitude. We're just looking at the magnitude and we're not looking at the direction at all. Is the magnitude of P, or the magnitude of vector P, equal to the magnitude of vector Q? Is this size of this vector equal to the size of this vector? Well, this is an equilateral triangle, so yes, that's true. P to C, so this vector here, is that equal to R? Well, they're the same size, the magnitude is the same, but the direction is not, so these are not equal. Next one, D to B. We're looking at this vector here. Is this vector, I'm not doing a very good job drawing my vector, is this vector equal to Q? And well, they're the same, the magnitude is the same, the direction is not, so false. So next one we have E to D, vector E to D. We're looking at this vector here. Is that equal to P? And it is, so true. The next one, vector P, is vector P equal to vector Q? Same size, magnitude is the same, direction is not, so false. Moving on. we have a hexagon over here, and it says here it's a regular hexagon, which means it doesn't look like it, but all of our angles are the same measure, and it's a regular hexagon, so the lengths of the sides are the same length. And then it says write down the vector which originates at B, it starts at B, and terminates at C. So we're looking at this vector here, and that would just be B to C. The tail is going to be at B, and the head is going to be at C. So is equal to A from A to B. This vector from A to B, what's equal to this vector here? Well, vector E to D is equal. So E to D. Part D says, B, I'm sorry, write down all the vectors which are the negative of E to F. So from E to F, the negative vectors of this. Well, the negative vector of E to F is going to be F to E. The negative vector is also going to be from B to C. So B to C. All right, has the same length as E to D. So we're looking at the magnitude. The magnitude, what vectors have the same magnitude of E to D? Well, this one, how about D to E, or F to E, vector F to E, or F to A, or A to B, or B to C, or C to D. All these would be examples of vectors with the same magnitude. Then it says write down a vector which is parallel, a vector that is parallel to the vector A to B. So the vector that's parallel to this, well, the vector that is, and twice its length, well, that would be then 2 times AB, or 2 of our vector E to D. Those would be examples of a vector that's twice the length of this vector AB. All right, so let's look at another problem. It's here. It says use the given vectors P, Q, and Q to construct P plus Q. So all we're going to do is we're going to move the vectors so they line up from head to tail. So we have our first vector, vector P, which goes 1 over and 3 up. This vector here, this is P. We're going to line it up with our other vector, which is 2 to the right and 2 up, 2 to the right and 2 up. The resultant vector is going to be this vector right here. We need to make sure that, because it's a new vector, we need to make sure that there is a head on the vector as well. So this vector right here is P plus Q. All right, the next one, line these vectors up from head to tail. So we have vector P, 3 over and 3 down, 3 over, 3 down. So this vector right here is vector P. Line them up from head to tail. Our other vector is 1 to the right and 3 up, 1 to the right and 3 up. So our resultant vector is this vector right here. This is vector P plus Q. Our other vector, well, we could almost use this already, but it looks like these vectors, so they're not lined up from head to tail. So we need to rearrange them so that they do. So here's a vector, 1, 2, 3, 4, 5 to the right, 2, 3, 4, 5. This is P. We're going to line up the head to tail. This one is 2 to the left and 3 up. So 2 to the left and 3 up. Now we have them lined up from head to tail. This is Q. Our resultant vector is this one here. This is vector P plus Q. We're doing the same thing with these ones. This vector P is 4 over and 2 up. So 4 over and 2 up. This is vector P. Our vector Q is 2 to the right and 1 up. 2 to the right and 1 up. So it's already, this is Q. So all of this is vector P plus Q. The next one, part E, we'll line these up again. So our vector P is 2 to the right and 4 up. 2 to the right, and 1, 2, 3, 4 up. We're going to add it to this vector here. This is 1 to the left and 2 down, 1 to the left and 2 down. So our resultant vector is this vector right here. This little vector right here. This piece right here is vector P plus Q. Line these up again from head to tail. This first vector P is 2, 4, 5 to the right, 2, 4, 5 to the right, and 3 up, 1, 2, 3. This is vector P. We'll line it up from head to tail. This other vector is 3 to the left and 3 up, 3 to the left, 1, 2, 3, and 3 up, 1, 2, 3. So our resultant vector is this vector right here. This is vector P plus Q. All right, continuing, I want to make sure this video is under 20 minutes. I still have 4 more minutes. So it says find a single vector which is equal to, we have this vector A to B and then plus B to C. Well, there's no geometric image here, but I can imagine that there's one. We could say that this is A and this is B, and so we're drawing a vector from A to B. And then we have another vector from B to C. So C is somewhere else. I don't know. It could be over here. It could be over here. It doesn't really matter. C is over, we'll just say over here. And so our resultant vector is going to be here, which means we are going from A to C, which means our resultant vector can be written A to C. Our next one, we have a vector B to C plus C to D. So again, we'll do some point B to C. So we have this vector. And then we have another vector from C to D. So D is down here maybe. And so our resultant vector is going to be this one here, which is a vector from B to D. So B to D. Now the orientation doesn't matter. This is just helpful for me. So just for understanding, I'll find some other point. We'll say A is down here and B is here. So this is A, and so we have this vector here from A to B. And we're adding it to another vector from B to A. Well, A is back down here, so we're going back down to itself. So if we have both of these vectors acting on, say, a sailboat, we have our sailboat is being pushed by this vector upward, but we have another vector pushing the sailboat back down, and so from an outside point of view, we don't see the sailboat move in any direction. So this actually becomes a 0 vector. All right, the next one, we have vector A to B. We have this vector here. We have another vector from B to C. We'll say C is over here. And then we have another vector from C to D. Well, I don't know, D is over here, so D. And so the resultant vector is going to, well, if we have this vector plus this vector plus this vector, we have 3 vectors acting on our sailboat. We're going to get this new vector here, which is going to be a vector from A to D. So there you go. All right, 2 more. We have A to C, this vector here. We have a vector from C to B. We'll say B is over here. So we have this vector, and then B to D. D is down here. So our resultant vector is going to be this vector here, which is A to D. And our last one, I have a vector from B to C, B to C, this vector here. I have a vector from C to A, this vector here, and from A to B, we're going back here, which means, again, if we have, oops, that one didn't really show up. There we go. So we have vector A to C, from C to A, from A to B. Well, again, our sailboat, with all 3 of those vectors acting on my sailboat, I don't really go anywhere. So this is, again, a 0 vector. I hope this instruction helped you, and best of luck.